Let me try if I can share. Or share the try later.
You can try.
Yeah. Okay.
Hello.
Hi.
Uh, Hello, everyone. I had a power cut on the boat yesterday, and apparently the internet took a massive hit, so it's not great today. But I hope it's gonna.
Oh, not.
Okay, Stephanie is no, because I was worried that my internet was stopping, so it's Stephanie.
Yeah,
Okay.
it's Stephanie issues.
Stephanie.
Lost Steph again?
Yeah, she's
Um,
on the boat.
on the boat
Mm.
today.
So maybe the valvefish ate the
And
connection
I'm
fibers.
also gonna record this just in case.
Oh, you was lagging for like a minute, Steph.
Hmm.
Yeah, it's not great. But I'm recording just in case we get cut off. And I make you the host. There we go. And then I'm just gonna leave it to Lee.
Okay.
Just in time.
I share this video. Let's see. I'm also like host now, so I'm admitting people in the same. So let's see if I can do. Okay. So yeah, we lost Stephanie. I just go. I chose this paper that is talking about imaging and genetics, which are two topics that I'm really interested in. And in particularly, they also use the framework of Alzheimer's disease. So in this paper, they try to apply a different method because they wanted to kind of like find statistically a causal relationship between genetics and imaging. And for doing that, they use like a kind of a complex statistics, but the main idea is that when you have many variables, it could be that, and you want to do correlations, it could be that these variables, let's call them instrumental variables, they are changing together. And so this could be a problem in the assumption of some statistical models, like Mendelian randomization, which tries to do a step forward just to do a correlation, but they try to say, okay, so this is causing the genetics is causing these imaging phenotypes. To try to answer this question, they are changing a bit the schema. So usually when you do imaging GWAS, meaning you are correlating all the genetics variables to imaging phenotypes. For example, in the UK Biobank, you can download and use in the platform these imaging derived phenotypes, which could be the fractional anisotropy of a tract, the volume of another brain region, so specific informations about some brain imaging details. However, if you put all this information that are a lot, which is great because you have a granularity of information, but if you put all these informations in a correlation matrix within modalities, so here you have structural MRI, diffusion MRI, fMRI, you can see that you have blocks. So let's say in Alzheimer, if more than one region is being reduced, so you have atrophy, you could be that there's not just one region, but maybe a lobe, let's say, or in diffusion MRI, similarly. Here you have also like a positive correlation and also an inverse, like a negative correlation, which is interesting when you think about crossing the tracks. So if one is impaired, maybe the other, but this is nice. And also fMRI, which is a bit noisier, but also here you can see some correlation within the modalities. So, what they try to do? They try to put all these imaging derived phenotypes, EDPs, within one modality. So, they are creating a unique information for each image phenotypes, and then they correlate the genetic part. And so they use the SNPs, the single nucleotide polymorphism, so one invariant in a specific position in the genome, and try then to also assess the phenotype that in this case is Alzheimer's disease. And they use the summary statistics, so people that already did this correlation here, so going through the genetics to the phenotypes, which is in this case Alzheimer's disease. They use these summary statistics that they already be run in the UK Biobank, and also the I don't know how to pronounce it, EGAP, the EGAP consortium, which put together some European cohort, some like the charge cohort, the ADG, which is the Alzheimer disease genetic consortium in Alzheimer with the genotyped data, which is kind of like one of the first data set in the States. And so they try, yeah, here they do some simulations because basically what they want to avoid is this false positive rate. So, and to have like a high signal. So they try to do some simulation, compare the statistics. But jumping a bit through the results because here we don't have a lot of time. They here show some results. So you have this kind of GWAS. So here you have all the genome divided by chromosomes and the correlations in this case. So putting together all the information of one modality. So here you have this big consortium, the EGAP, let's say, for structural MRI, diffusion MRI, fMRI, and then they also reproduced in the UKB the same approach. Really interesting. They found in chromosome 19 a lot of signal, which is where you have all there is also the APOE, which is the highest signal usually in GWAS. That here, I'm not really sure that, yeah, Tom 40. So, yeah, that is the APOE locus. So, super strong signal there. And sometimes you also have in chromosome 8. And you have it for the structural MRI, the diffusion MRI, these two chromosome signals, but not for the functional MRI. Same in the UKB, you have signal for the structural and the diffusion. The chromosome 8, here it's missing, here is present, and the fMRI again, no signal. Then they also try to change a bit the model and so be a bit of less restrictive. And they also find some signal in chromosome 2, and again here also something chromosome 19 for fMRI. So this is also encouraging for fMRI. And you can be always generally less signal here just for the diffusion MRI. And they also do some considerations about these results. Yeah, one that a lot of people like, yeah, we are conscious is that in the UKB, people are generally younger. So the mean age is 56. In the EGAP is higher than 65, which is good for Alzheimer's disease because it can present later in time. And also the proportion, the enrichment of AD cases, which in the UKB is not, so the UKB is more for the general population, it's not target for Alzheimer's. So of course the AD cases will be less than Alzheimer, like the EAP initiative that is like for Alzheimer. It's normal that you can have more signal generally. And for fMRI, I found encouraging that at least they found one signal, really strong for diffusion MRI, which is great because it's a modality that I really like. But also for structural, you have this signal. So I can keep talking, but I don't know if maybe I should stop and we can discuss. Mm.
As you prefer, if there is something that you would like to also mention before we jump into discussion. If
Miss-
not,
Yes, so in the discussion, they also touch other points. Yes, there is also this, they also suggest that, yeah, they found one way to address this collinearity that is called horizontal pleiotropy when you are using more instruments that they can covary together. So they try to fix that. Then you have also this vertical pleiotropy. So it could be that there is also correlation. You're using the same brain between, for example, structural MRI and fMRI. No, structural fMRI and also diffusion MRI maybe could be more straightforward, but also fMRI. And so they didn't consider that. They point out to other methods, like SUSY is another method that I've been using, for example, in proteomics, that kind of do these corrections for false positive afterwards, the first correction, so it's a second step. Or also they also point out to dimensionality reduction, which is also something that I work on. So this could be also another way to extract one information from one image. So the same modality, kind of put all the information together. But for doing that, you need the raw data, and usually these are not available. And the majority of the case, then if you start a collaboration, something, then you can also have raw data, I believe. But generally, you have just these summary statistics of like information about the volume of some regions, diffusion metrics on the tracks, and so forth. And yes, so maybe if you have some discussions, some questions, we can also
yeah.
discuss it together.
Thank you, Leah, for presenting. I'm taking over Stephanie because she
We
has
lost.
technical issues at the moment, but there are already some hands up, and I think first was Erwe, maybe. So, so go ahead.
Yeah, thank you, Leah. So yeah, very interesting to see some papers about genetics and neuroimaging always. So my question is, so I have other questions, but I didn't dig enough in the paper to get all the information, but a very simple question, yeah, very maybe to start the discussion. So, do we have to give up on the functional MRI and genetics So based
Uh,
on the graphs, because I was looking at
yeah.
one, there is nothing. So I was surprised to see that.
So here there's nothing if you really correct for all the issues. But I found encouraging that at least they found one signal
Okay.
here in the like removing some of the restrictions of on the collinearity. They found a signal and it's not a random signal. He's here in chromosome 19. That is the signal that they found more consistently and that we know genetically is important. And in the EGAP consortium, so enriched by Alzheimer cases. So I think that also fMRI can give us some information, but of course, as we know, it's noisier and maybe there is, I don't know, we need to do something more specific for fMRI, I believe, something more target for this modality.
Yeah.
Uh, just taking some informations of principal component of the fMRI, I don't know, maybe it's not enough, but it's giving the right signal here, so it's not random.
Okay. So is it resting state only, or is it task-based fMRI, or
I don't know what did they use exactly. Probably.
the
Mhm.
simplest will be resting state? I mean,
I believe so, yes. But there was a point in the paper where what was that? Where they discussed the imaging, fMRI imaging modality. Here's the introduction. Here is the methods, where they talk about the data set at some point. Here, data analysis. So here, okay, here they discuss the volumetric, I remember, the diffusion MRI. Where was the
Yeah, it's
fMRI?
resting state. It's at the top of the page.
yeah.
Ah, okay. So if I did, I believe it was resting state, yes, but I want to double check. Yeah.
Yeah. Okay. So they look at the connectivity matrices, and okay. Okay. Well, maybe yes, as you say, maybe some more work.
Ah, here, yeah.
Yeah.
210 resting state functional connectivity metrics from resting state fMRI.
Okay.
Yes, I believe that yeah, maybe something more target. I don't know. You have these feelings, or maybe you need statistics that it's more target to some issues that you can have there. But they at the end they at least found a signal, so this
Yeah.
is encouraging somehow.
The graph you showed, the second one was after correction for collinearity. It's what you said,
So
this one?
this one was correcting for everything, and then they used these no adjustment for horizontal pleiotropy,
Okay.
and there they found a signal in the fMRI dataset, the modality.
Okay. Because it's a correction. How do you explain this effect? It's because they separate the effect of the other modalities, and in this way they can adjust the functional MRI signal to be more
So
sensitive.
basically, they kind of say like, yeah, we cannot use all instruments, so like each columns like here and here like separately as you do usually, and so because they covary together, we have a collinearity,
Yeah.
and so they kind of use it as as a vector, so putting all the information together, and so you have one variable, to my understanding. So you have like one variable at the end. So you don't do the sum of each of the effect, but you put it like all together in a vector. And so somehow you are clumping the imaging information all in one and see if you have a signal in that correlation with the genetics. So it's here you see you have all the ADPs, you put it all together in one block, and so you are having one modality, and so then you have the GWAS for each modality.
Okay. Okay, I see.
Mhm.
Thank you.
You're welcome.
Okay. Next one was Chris. So go ahead.
Thank you for presenting that. So it is targeted on Alzheimer disease phenotypes, right?
Yeah.
Do you think so? The imaging parameters that might be associated with the genes, or the genes are associated with the imaging parameters, they are in this context specifically, but that doesn't mean that if there is no signal with one modality, for example, if we were studying another disease, we might have a signal, right? Or
Yes,
is it
yes,
more general than that?
definitely.
Yeah.
Here they test so the causal the causality of the correlations with Alzheimer disease, and so it's also like I expect there should be like a different signal if you are analyzing Parkinson or autism, or here they just tested Alzheimer disease, and they use it taking the summary statistics of this correlation in blue that already have been computed. So yes, they just test one modality. Yeah, it would be nice to see at least one disease, at least another phenotype, which could be also the BMI. It could be like a lot of like the longevity. So you can test everything as a phenotype. Yeah.
Yeah, that would be interesting. But do you think so Alzheimer, the genetic aspects of Alzheimer is studied a lot compared to other diseases. I know, for example, in stroke, stroke has many different comorbidities, and the genetic aspect is not as direct, I guess, as for Alzheimer's. But yeah, do you think that would translate well? So of course you would need the database. That's why with Alzheimer is ideal, because this genetic aspect is a very common direction. But for stroke, for example, we don't have that much genetic data. But if we had similar a similar amount of data, do you think that could be done in other diseases with the same methods, or do you think
Yes,
it?
yes,
Yeah,
I think that you can do it. And also for stroke, you will be surprised, but there is there is a website that is called the GWAS catalog, where you can download freely all these summary statistics. And also for stroke, you definitely have some signals. There are consortiums also for stroke and for other diseases. Maybe yeah, for Alzheimer, maybe we talk a lot, but there are definitely a lot of genetics data and
yeah. Now
studies
there is,
out
but
there.
when I see the data set, was it like 40,000 data points? I've never seen that in stroke. In
But yeah, this
yeah,
approach, you just need the summary statistics, and you
yeah.
could then run it on the UKB for stroke, for example. So no, I think definitely you can translate it in other modalities.
Yeah.
And maybe I'm too optimistic, but for stroke, for sure. Like now, I don't have I don't remember by heart the number of stroke cases in the UKB. But yeah, one thing in stroke is that you could have heterogeneity, of course, of presentation with age, but you also have it on Alzheimer at the end. You can have also vascular components, not pure Alzheimer cases when you are
Yeah,
aging.
that's true. You have a lot of confounding, and like also like, yeah, all the diseases mixing up with each other.
Mm.
Yeah,
So, I mean, definitely it's worth trying, I believe.
yeah.
And yeah, like stroke, Parkinson, these are all phenotypes that I would investigate, definitely. I think we have enough, we should have enough data now. Or for sure, we have summary statistics of a big consortium that you can use. Mhm.
Okay. Uh, if no one has any other question, I have a question. So it's more about methods. Maybe I missed it. So, but I do remember you saying that they're trying to find a causal relationship.
Mhm.
But in the methods, I didn't find nothing that being causal. It's more like correlations or, yeah, right? So like finding some
Yeah.
relation. So what do they mean by causal relationship if this is just, summary statistics and relating different modalities with each other? Or I missed something in an.
Yeah, you're right. I think it's a bit hidden somewhere. So usually when you talk about causal relationship, you talk about here they use in the introduction mention the Mendelian randomization somewhere. So instruments, when you have this terminology of instrument variable, is referred to Mendelian randomization that is put it here. But it's more in the introduction as one of the methods. They mentioned this brain X scan that actually I never used. But then in the formula, I also missed a bit this information. Maybe I was lost, I don't know, or they didn't put all the information, but I believe they should use this kind of like instruments approach because they also mention in the abstract this Mendelian randomization, and usually you have it when you see here there are three steps of like you have this correlation and then there's other correlation. And so this is really typical of the Mendelian randomization
But
like statistics.
I'm not really aware how it works. Like, is it just randomizing the variables and then correlating, or like some sort of?
Um,
Because if it's just randomizing variables, in the end, it's still a correlation, right? So like,
I'm not an expert in material optimization. I start to look into that, but they look more if the effect is maintained
mm,
in these like two steps.
mm,
So they kind of like try to get rid of some confoundings, and so the correlation is in both direction, and they try to find just one direction. And for doing that, they compare the effect size of these two steps. Maybe I'm not the best in explaining these modalities, but these statistics, but I believe they use this approach even if I didn't real. They mention a lot of things. They mention also like some feature extraction, like Elasto in the introduction, SCAT, but maybe I didn't read the
mm.
paper so in depth.
Okay.
But somehow also look into the introduction to the abstract. I believe they go towards this like model also because they use these two steps. So somehow they kind of they want to see a correlation that is maintained between the SNPs, the imaging, and also the Alzheimer. And then it's not just between all of them. So it should be in one direction.
But then it's still a correlation, am
Yes,
I
of course.
wrong?
We are doing
So
correlations, yes.
yeah, so I thought when I read causal, maybe in that field it's interpreted as gene causing something, but in the end, methodologically, it's not a causal relationship because,
Ah, no, I mean, they
right?
are
Yeah,
trying to
yeah,
correct
yeah.
for what they call pleiotropy. So you can have some effects that, for example, the typical example of pleiotropy is that you have the ApoE that is causing also like some cardiovascular risk factor, also Alzheimer, and so then you don't know if ApoE is causing just Alzheimer or ApoE is causing like vascular risk factor. Those are causing like they are boosting the other or the other. So you're trying just to have a pure correlation in one direction. And so you kind of get rid of triangles or like spurious. And so you say, okay, so if that correlation is just in that direction, we can think is causal, but it's still a correlation.
Exactly. Yeah. Okay. No, but thank you a lot. I will also look into this Mendelian randomization. Never heard about it. So
Yeah, it's really in the genetical field. I also
cool.
approach it in that way. Maybe in imaging we have do more a Bayesian approach. Maybe it's more trend in imaging, but you can have also this. There are also in R. You indeed also this brain X can. I look it quickly and was an R packaging because yeah, you have some R packages for that. But yeah.
Okay. Well, amazing. It's 10 o'clock. Thank you, Leah, for presenting, and for everyone for having a discussion. And see you next Monday, 9:30 as usual. So, bye bye.
Thank you so much. Bye.
Okay. Bye bye.
Bye. I'm sorry we lost Steph.
No, it's okay. How are you?
Me, good, good. A lot of things. I was in Bordeaux like
Nice.
last week. Now I'm in Italy. Now I'm late to go to Parma. I'm always
Okay.
Again,
in between things. Oh, Steph.
Hey, sorry. Can you make me... hang on. I think I can. Yeah, no. Can you make me host so I can stop the live stream?
We can make you. Can I make you? Go. More. Spotlight. Put all to record. Remove. How can I make you host? Can I make you host? Or really, can you make?
So if you click on her image on the right side where there is also like mute, there are
Yes.
also three dots, and there has to be like make host.
I don't have make host. I have chat, stop video, pin, spotlight, rename,
You
allo,
can see
remove.
the YouTube on the top and you can stop the stream.
But maybe she's not the host.
You're
Maybe.
the host, Lilith.
Ah, you are. I'm the host.
Here we go.
Okay.
Thank
Okay,
you.
I was